All right, section 1.4. Don't ask what happened to section 1.3, just like we don't ask what happened to the old Taylor. So, here we go. We have complex numbers. Complex numbers, let's just say early on, are any number that can be written in the form a plus what we call bi. Now, in other words, a complex number has a real part and an imaginary part. So, it looks like it's two distinct things, but mathematicians refer to a plus bi, or in other words, let's even look at your example number 1 here. Why would we write it like this with parentheses? Well, we as mathematicians are trying to say this is complex number 1, or like, in other words, this is the first complex number, and I want you to subtract this second complex number. And in parentheses, that's what we're denoting, is this whole thing is complex number 1, or the first complex number, and this is complex number 2, or the second complex number, and we're subtracting them. Now, what we need to spend a quick second on is, well, then what does that make I, and why is this part imaginary? Well, I is what you get when you, as a mathematician, square root -1. Now, don't type that into your calculator unless you have a special one. Most calculators, when you type the square root of -1, will just say, domain error, can't square root negatives, or something like that. Or, just some sort of error message. Now, as mathematicians, we see that error message that you can't square root negatives, and we evidently, and honestly, this is all baked into, I don't have a physics degree, but trust me that I do know from my many years that there are many applications where these complex numbers, these imaginary numbers that we think, you think, don't matter, power your life. Wi-Fi is one of them. So if you enjoy having your Wi-Fi, these complex or imaginary numbers that mean quote-unquote nothing are what make your connectivity, your GPS, electronics all work. They all end up having calculations that involve complex numbers in their early stages. And, be a physics major and come back and tell me precisely how that happens. I just know that it does. And you gotta trust me. But from there, then, if I is the square root of -1, or in other words, if I is there to, and catch this argument, represent that I know that I can't square root negatives, but if I could, let me just put a symbol on it, then what would I squared be? Now, I squared, well, think about it. I is here on the left, I squared is here on the right. There's an equal sign, and there's a square root here. And we learned that if you have a square root, and I square both sides, they should, quote-unquote, cancel out. So I squared is -1. Now, in other words, if you look back to our first notes, we kind of looked at this. We looked at the square root of -49. I'm pretty sure it was that, or maybe -36. And we just said there was no answer. And what we were saying was, well, if I take -7 times -7, that would be 49. If I took +7 times +7, well, that would be 49. So there's no two real numbers, notice there's no I here, that can give me +49. Or there's no number I can square that gives me a negative. But look at this. You can square this special number and get a negative out of it. Now, in other words, in this class, all you need to know is that when you see I squared, you're going to replace it with -1, and you're just going to remember that I itself is the square root of -1 by itself. And you can kind of see this, what I'm going to call technical note. In most cases, I is going to be no different than a regular variable, and let's even see that in the first 4 examples. These go by pretty darn quick. So, I've got 3 plus 9i, and why am I just copying that? Well, because parentheses with no number in front and no exponent, don't need anything else done. Now, the second one, because there's a negative in front of parentheses, I need to distribute that negative and change both signs here. And so this is what I get. And at this point, this is my kind of big argument here. Now I just have like terms to combine. So I've got a 3 and -4. Well, that's -1. I've got a 9i and a 7i, and that's 16i. And guess what? I'm done with this problem. So if you're sitting there going, what on earth was he talking about for the first 4 minutes? That's all I'm doing. Good. In most cases, that is all you need to worry about. Again, somehow, trust me, this powers cell signals, electrical currents. Many, many different wave things that we study involve complex numbers. But we just deal with the mostly simple cases, although there will be a few funky ones coming up. Well, let's see what happens next. Up next, I've got some distributive property to do here. 4i times these two things. Well, let's see what I get. I get negative 8i. But then I get, here we go, 12, and then I times I is I squared. Now, that was the warning, is that when you see I squared, know that that's negative 1. I've gotten into the habit of whenever I encounter I squared, I'm going to circle that term that had it. It's just my kind of practice or what I did for myself, and it helped. So let's see what I have now. I've got negative 8i, and then this, because this is, catch this, plus 12 times negative 1, then this must be, let's see here, 12 times negative 1, this must be negative 12. And I'm almost done, but as mathematicians, we write the real part first and the imaginary part second. And there we go. All right, let's keep on going and see where we go. We've got some foiling to review now. So first we've got 2 times 5, that's 10. Then we've got the outer, the farthest left, farthest right. 2 times I is 2i. Nothing shocking so far. I then have the inner, negative 4i times 5, and that's negative 20i. And then I've got negative 4i times positive I, which is negative 4, and then I squared. Now once again, once I encounter my I squared, I'm going to circle that term. Okay, what do we do from there? Well, I've got my 10. I can combine these two, which will make negative 18i. And then I've got a negative 4 times a negative 1, because I squared, remember it's up above, but I'm not going to go back to it, is negative 1. So negative 4, negative 1, multiply to make positive 4. I think it said negative 4. Negative 4 and negative 1 make positive 4. And from there, well, 10 and 4 make 14, real part first, and negative 18, I just tags along at the end. And this is my final complex number. Okay, now let's keep going. I don't want to make a big conclusion yet. Let's do some more foiling. We're going to do this one a little bit quicker. So that's going to make 9 from the first. That's going to make negative 15i from the outer. That's going to make positive 15i from the inner. And that's going to make negative 25i squared from the last. So we're just doing foiling what we reviewed early on. And now let's see what we get. Well, the negative 15i and positive 15i cancel out completely. Negative 25 and I squared, that's another special one. That one's going to make 25, positive 25, because that's negative 25 and negative 1 multiplied together. And that's going to give me 34. And this is where I'm going to stop, pause, and talk through our first few examples. Here's what we found that sounds kind of interesting. If I add or subtract complex numbers, I may get another complex number. I could get just a real number or just an imaginary number. If I multiply, hear this, only an imaginary number to a complex number, I could get another complex number or maybe just a real number or maybe just imaginary. But in this case, I got a full complex number. In this case, I multiplied two complex numbers and got a new complex number. Now finally, I multiplied two complex numbers and I got a real number. And I can tell you this only happens in real, there's the dumb pun of the day, a real special case. And it's because this is what we call conjugate pairs. It's where the first two terms, or rather the binomial structure, if I want to use my real professional math words, this two-term structure and this two-term structure are identical except for the sign switched between them. Those have a name in mathematics. We call them conjugate pairs. Why would we give them a name? because of what just happened. Two complex numbers that were conjugates multiplied together and became a non-complex or a regular real number. Because of that special behavior, and that only happens where there's a two-term structure with the sign switched in between, we decided to say complex numbers that are opposite signs between, let's give those a name. And we'll call them conjugate pairs. And we'll see those more throughout the course, and I think we even reviewed them earlier, but hopefully that definition sounds familiar again. If not, we'll see it later. Now, these next examples are where things get a little trickier, unfortunately. We might have to slow down or spend a little bit more time, but hopefully it's not too bad. Now, in number 5, we did do this in review. We have, unfortunately, some rationalizing to do. Now, here's the thing. Nowhere in this problem is it directly saying rationalize. However, there is a question on the page and we need to know what to do. Now, what we need to do is we need to get rid of the I, or the square root, that's when we rationalize, from the denominator. And in fact, now I know we've talked about conjugate pairs because we talked about how to deal with that. I'm going to multiply by the conjugate of this denominator. Now notice I'm multiplying the whole fraction by that because, again, we're only multiplying this whole thing by 1, just a very, very special choice of 1. Let's see what happens when I distribute in the numerator, because there's only one term up here. When I distribute, I'm going to get 14i. I'm going to get 7i squared. And on the bottom, let's see what I'm going to get. I've actually got some full foiling to do. I've got 4. I've got positive 2i. I've got negative 2i. And I've got negative I squared. Always circle your I squareds. Always circle your I squareds. Sorry, I went off the page there. But there's what I get for my initial foiling. Let's see what I do now. Well, because of my foiling and because of my conjugate pairs, that's why I chose this, is because it is the conjugate pair of my denominator. These cancel out. Now I'm going to do some shorthand here. A positive 7 and an I squared make negative 7. And a negative I squared make positive 1. All right, pause that. Think about that if you need to. And then let's see what I finally get here. We're pretty much there. I have a negative 7. I've got a plus 14i. Just reordering that. And then on the bottom, I've got a 4 and a 1, which must make 5. And there we go. I have rationalized this question. All right, number 6 is a little bit trickier. And at this point, honestly, I kind of want to say, well, never mind. We're 13 minutes in. We can do it. So let's press on and get through this one. We still need a conjugate pair. Now watch this. It's going to be negative 4 plus 2i. And this is, I put this problem in here intentionally, and this is why we're not skipping over it. The reason I want to call this example out clearly is because a lot of students hear me say that the conjugate is just the sign in between switched, and then they second guess themselves on this example. But notice what I did. I did not change the sign in my denominator on the negative 4. It's only the sign between the first term and the second term that changes. And again, when you multiply that conjugate, it's the same on bottom and top, so that you multiply by, if you remember this argument, so that we multiply this whole thing by 1. We are not changing this problem's worth, we're changing its appearance. This ugly thing over ugly thing is 1. Because anything divided by itself is 1. We're just making a very, very, very careful and precise and interesting choice of what 1 is, and we're going to multiply conjugates and see that i's disappear from the bottom. Well, let's see how they disappear from the bottom, and let's FOIL out carefully. Now, I have actually true foiling to do on the top and bottom. Watch me talk through it. Now, that is negative 4 here, just to be careful. Let's see what happens. 2 and negative 4, negative 8. That was in the numerator. 2 and 2i is 4i, still in the numerator. 3i and negative 4 is negative 12i in the numerator. And 3i and 2i is positive 6i squared. And I'm even going to circle that now just so I don't forget about it later because I squared is special. On the bottom, negative 4 is positive 16. Now here's a vocab lesson. If these are conjugate pairs, do the outer and inner matter? The answer is no, and that really is a vocab question, but let's see what I mean. Negative 4i, 2i make negative 8i. Negative 2i, negative 4i makes positive 8i. These cancel. That's what I meant. The outer and inner won't matter when you have conjugate pairs. And then negative 2i and positive 2i is negative 4i squared. Circle it because I squared is special. All right, let's see what we have and let's wrap this up. And we're going to wrap this up kind of in one step, but if it takes you a few more to write it out, that's fine. I'm just running a little bit out of space. This is negative 8. This will be negative 6, so I've got negative 14 in my numerator. I've got a 4i and a negative 12i, so that must be negative 8i in my numerator. In my denominator, I've got a 16 and a positive 4, and that's 20 in my denominator. And man, I thought I was done, but I'm not, because unfortunately 14, 8, and 20 can all reduce. And that is my final answer. That honestly might be the nastiest problem we've seen so far. But well, let's see if it gets worse. Sorry that that's not more positive, but that's my sense of humor. All right, let's keep going. Up next, here's a kind of funky problem, but let's work through it. First thing we got to realize is that this is saying what is negative 3 minus root 5i times itself. So what does it mean to square something? It means to multiply by itself. What does it mean to have, now catch this argument, a negative inside your root? It means you have I that you can take outside of the root. Now notice that the I is outside of the root. It's not under the hood of the root, so to speak. Now also notice that the negative on the 3 is still there intact. The negative out front of the root is still intact. It's just the negative on the interior of the root got pulled out and called I explicitly. From there, we've got some foiling to do. Negative 3 times negative 3 is 9. Negative 3 times negative root 5i, oh gosh, that's a mouthful, is positive 3 root 5i, and that's a handful to write. Up next, so we did the first, we did the outer, let's do the inner. Negative root 5i times negative 3 will be positive 3 root 5i. Now, also, what I'm kind of telling you is that usually the order we write things in is number, root, I. And then, finally, the last, let's see what's going to happen here. I'm sure this will be special. Is going to be positive, because that double negates, root 5 squared. We'll deal with that in a second, because it's root 5 times root 5. And also, it's I squared, because it's I times I. Once again, I'm still running out of space, so let's continue this down here. Let's see what happens. Well, this is going to be 9, still. 3 root 5i, 3 root 5i is going to be 6 root 5i. Now, that sounds crazy, but let's say it like this. I've got 3 of this ugly thing, and I've got 3 of this ugly thing, so I've got 6 of those ugly things. That's all it comes down to. Now, root 5 squared is just 5. I squared is just negative 1. So, finally, at the end here, this must be negative 5. And so, my answer ends up being 4 plus 6 root 5i. Now, that's one I'm going to double check on myself because sometimes math happens. Thankfully, that one was correct. All right, let's keep going. We're almost done. This one, similarly, actually, there's a little bit of extra going on here. I've got a negative root 12. Now, root 12, this is the first time this has happened so far in this section, careful, is not only a negative and a 12, but remember that 12 is also a 4, which is a perfect square, and a 3, and a negative 1. So what do I mean by that? My first step here, catch this, is that this is really 2, because the 4 can root, root 3 because it's stuck inside, I because the negative was there, but now it's pulled out. And that's what negative root 12 becomes. And similarly, negative root 7 becomes, well, root 7i. The only I escaped. And finally, this root 11, well, that is just root 11. But the big concept there, or the big catch there, is that notice that this 12 wasn't just that I was the issue, it was that 12 has a 4 inside of it. And that's still a callback to what we looked at in our review section. Well, let's work this out quickly then. So 2 times nothing out front is still 2. Root 3 and root 7 make root 21. And I times I makes I squared, which we'll deal with in a second, and I'm going to circle it. Finally, at the end here, we've got 2 times, well, 1 out front is still 2. Root 3 and root 11 is root 33. And I times nothing else is I. And so I squared is negative 1. So this must be negative 2 root 21 plus positive 2 root 33 I. Goodness. So things are getting a little bit tricky, and I hope I'll see you in the next section.